calculations with significant figures. Now, when we do calculations in chemistry and we get a number in a calculator, it's going to have a lot of decimal places. And one of the things that we have to make sure of is that we don't report any more decimal places than necessary. And that comes back to significant figures. When we are adding numbers, 4.12 plus 6.559, if you punch that into your calculator will report 10.679. Right? If you were to write that down on a test, you would get a half mark deduction because you have failed to take into account significant figures. And that works like this. When I take 4.12 and I add it to 6.559, we're going to go back to elementary school for a minute here. I'm going to line it up old school. And then when we do this addition, we get 10.679. Now remember that in chemistry or in science, every number that you report is only allowed to have one value that has been estimated. So let's take a look at what happens when we do that analysis. In 4.12, the estimated value is this number 2, which makes this number 7 an estimated value because there is some error that's coming from that 2 up top that's going to come into that 7. In the number 6.559, the 9 is an uncertain value. That is the number that you estimated, which makes this number 9 also an estimated value. And so there we have our problem. In our final answer, 10.679, we have 2 estimated digits when we are only allowed to have 1. What that means is we must cut our number off. We must report our final answer right here after the 7. So our actual answer is going to be, whoops, I hit myself there, is going to be 10.68. Now that 9, that is an estimated value, we can utilize that number to bump up the digit right before. We can round the next digit up. And we can do this and we can still be sure of our accuracy here, because although we're not really sure that 9 is indeed a 9, you've guessed that it's a 9 and it's way above 5, and that gives you a reasonable amount of, a reasonable reason, if you will, to round the next digit up. The other way to think about this, to rationalize this idea, is that when we add 4.12 to 6.559, there's no value here. Okay? What is that value there? You might be tempted to say 0, but actually it isn't. Because in our ruler, we may have not had enough lines or increments on that scale for us to read if that was a 0 or not. It may have been a 5 for all you know, it could have been a 9 for all you know. And so for those reasons, 9 added to a number that simply doesn't exist for us is not 9. It wouldn't make sense. And so that's another reason why we would cut the final answer off to 2 decimal places. So the rule with adding and subtracting is we always round the number off so that the decimal places in the final answer matches the decimal places of the number you used that had the least number of decimal places. So let's look at 9.1 plus 11.8489. You can do this on your calculator, or you can do it like this, but use your calculator, okay? I'm just doing this to illustrate a point. We do this, we carry all the numbers down, we get this answer here. Our final answer needs to be cut off right here. Because this 9 is our first estimated value, this 9 is estimated, which makes this 9 estimated, but we are only allowed to have 1 estimated value in our final answer. So our final answer is going to be 20.9. Okay? So our final answer has 1 decimal place, because in our original question, the number with the least number of decimal places was this one, with 1 decimal place. Be careful when you are adding numbers with that are represented in scientific notation. It will be incorrect for you to line the numbers up like this and add them, because the first number is 10 to the negative 5 and the second number is 10 to the negative 3, which means that the decimal place is not in the same place for those 2 numbers. what you want to do is you want to pick one number and convert it such that the power of 10 matches the other. It doesn't matter which number you choose. Okay, so let's choose the first number here. 6.22 times 10 to the negative 5. How do we change this 10 to the negative 5 into a 10 to the negative 3? We want them to match in order for us to do this decimal alignment step that we do for addition and subtraction. Well, right now, 6.22 times 10 to the negative 5, the negative 5 says this number, the decimal place is actually shifted over 5 times to the left. If I want this number to be shifted over only 3 times, the decimal, excuse me, that means that I have to actually move the decimal over twice myself, which means that this is going to be 0.0622 times 10 to the negative 3. Okay, so we get 0.0622 times 10 to the negative 3. Okay, now we can align our decimal places. Now we can do our addition here. Oops. And this gives us 3, 9, 3, 8, 6 times 10 to the negative 3. And this would make sense. This 2 here is our first estimated value for the top number. And this 1 here is our next estimated value for the bottom number, which makes 3 the estimated value. And we are allowed to have 1 estimated value in every value that we report. So that is indeed the final answer. Final answer with 5 significant figures. Multiplying and dividing is another set of rules. When we punch in the numbers 5.1 times 5.1234567, our calculator is going to report to us that our answer is 26.129629917. Where do we cut that number off? Well, it works like this. Between the numbers 5.1 and 5.1234567, which one is the more accurate of the two? This one. Okay. This value is more accurate because it's got more decimal places, which means it came from an instrument that had a lot of increments in it and a lot of lines for you to read the decimal places to that far. So that comes from a very accurate measurement tool. The 5.1 comparison is not as accurate, which means that when you multiply these two numbers together, the final answer cannot be more accurate than the least accurate number. And then repeat that and just think this through. The final answer cannot be more accurate than the least accurate number that you used in the calculation. Which means that our final answer here cannot be more than 2 significant figures. This number has 2 significant figures. This number has 8 significant figures. 8 significant figures is more accurate than 2 significant figures, but our final answer cannot be more accurate than the least accurate number. So our final answer must be written as 2 significant figures. In other words, when you are multiplying or dividing two numbers, your final answer significant figures must match the number you used with the least significant figures. In this case, it is 2. Let's look at another example. What is 9.000003 by 2? Your calculator will spit out the answer 4.50000015. When we look at our two numbers that we use to calculate this number has 7 significant figures. This number has 2 significant figures. Our final answer cannot be more accurate than the least accurate number, which means that our final answer is going to be cut off at 2 significant figures, which means it will be cut off at 4.5. That is to say, our final answer, the accuracy of the final answer, will be limited by that 2.0 that we used. Okay, so rules for adding, subtracting, and multiplying, dividing are different. Remember which rule belongs to which operation. when we deal with mixed operations, we have to keep those both of those rules in mind. Both of those rules in mind, which means that we have to do the significant figures set of rules multiple times all throughout our calculation. Let's look at the first problem here. When we add 2.1 to 9.000, we get 11.1. Okay. The zeros at the end here, I'm going to keep those in there because I want to be accurate with my calculation. I want to carry those through because I'm not actually finished with my calculation. But when I add those two numbers together, 2.1 to 0.000, the number should be cut off after the first decimal place, because in the addition rule, we follow the number with the least number of decimal places, which is 2.1. And so I'm going to write my answer to the operation in the bracket here as 11.1. That's where I should stop. But I'm going to drag those zeros down anyways, because I'm not yet done with this whole problem. In the second bracket, I get 2.33 plus 1.9841. And in my calculator, I'm going to get a large number here. Now, this is another addition problem. The number with the least number of decimal places is 2.33, with 2 decimal places. So I'm going to write down the answer to that with 2 decimal places. But I'm going to keep the remaining decimals in there as well. Now, this is because I want my final answer to be as accurate as possible, which means in my calculator, I must punch in every single digit that I have. So although the little 41 here is not significant from the operation within the bracket, we have to actually punch that into the calculator when we do our final multiplication step. Otherwise, we're going to be off by a few decimal places. Okay? So now I can go 11.100 times 4.3141. Again, I'm punching in that 41 there. And I'm going to get 47.88651. Then I'm going to think about my final answer in significant figures. The first number that I multiplied here has 3 significant figures. The second number I multiplied has 3 significant figures, which means in my final answer, I need to have 3 significant figures. And so it's going to be 47.9. So you see how we have applied the significant figures rules multiple times. We applied it once over here, we applied it once over here, and then we applied it one more time over here. So sig figs, the ruling for sig figs were applied 3 different times, but the numbers were not actually cut off or rounded off until the very, very last step. And that is important. If you were to simply go 11.1 times 4.31, you would have gotten 47.8. And you would have lost half a mark on being inaccurate. Okay? The reason why I write these numbers very small is to remind myself that from the bracketed operation, that 41 is not significant, so I write them small. I still punch them into my calculator though. Okay, next example. I'm going to do the first thing in the brackets there, 9.43 plus 4.1. My answer is going to be 13.53. The 5 is actually, we actually cut the number off from the addition step. So I'm going to write the remaining number as a subscript to remind myself to punch that into my calculator, but that number is not actually significant. Then this number is going to be multiplied by 4.3, and that's all going to be divided by 0.11. Okay. Now this is rather straightforward. 13.53 times 4.3 divided by 0.11. My calculator will tell me 528.9. How many sig figs should I have? Well, in the last steps here, it's a multiplication followed by division, and those two operations have the same rule, which is we follow the number with the least number of sig figs. And this number has 2 sig figs, and that number has 2 sig figs, and this number has 3 sig figs. And so our smallest set of sig figs is going to be 2. And so our final answer is going to be 500 430. That is how we write the number with two sig figs. We use that 8 to turn this 2 into a 3. Remember that trailing zeros are not significant, so 530 is a number with two sig figs. Or, what's often the preferred method, is we write 528.9 in scientific notation. When we do that, the decimal place must be placed after the first non-zero number, which is 5. The 2 is going to become a 3 for rounding. And then we multiply it by a factor of 10 to bring the decimal place where it should be, which is 2 times to make this into a 530 number. Okay? And that is the end of this unit. Sig figs, how to measure, how to convert units, and how to follow sig figs through to the end, okay? And just to recap one more time, never round off a number, never cut a number off until you've reached the final step of your entire calculation. Please give the fun sheets a try, and remember to check your answers, because if you don't check them, you don't know if you're right, therefore it's the same as not doing them at all. Make sure you practice that. Go out!